Yeah, welcome to this next lecture on Illumination Engineering and Electric Utility Service. This lesson 8 is titled Discharge Lamps I. In fact, we looked at the artificial sources in lesson 7 employing the phenomena of incandescence, which essentially looks at the materials being at a higher temperature. And here today we move on from the physical process of incandescence to the next level, that is electroluminescence, and we look at the discharge lamps employing electroluminescence. Therefore, the instructional objectives for this lecture would be: what are discharge lamps, state various types of discharge lamps, list types of emissions that makes a gas conducting, distinguish line and band spectrum. So, this is the issue that we are trying to use various physical processes, as already told in earlier lectures, that one is the incandescent, which we saw extensively in the last lesson, employing tungsten filament. It has gone through several stages. In fact, the Edison lamp was the incandescent lamp, which depended on the filament material maintained at a certain temperature. Higher the temperature, higher was the radiation output. However, as already told, any source we employ should be able to give good efficacy. We defined the light efficacy as the lumens per output of electrical energy, because you remember that most of these lamps are being powered by the electrical energy, and in fact tungsten filament and halide lamps, which are in vogue these days, come under the category of incandescence. The next particular phenomena that is employed is luminescence or electroluminescence, and as already told, it is the phenomena by which a radiation is obtained by creating a discharge in a gas or a vapor by the application of electric field, unlike the one in the incandescent where the filament material is heated, so it could be at relatively lower temperatures. In fact, that is one of the reasons why a discharge lamp is more efficient compared to the incandescent source. In fact, in going to the discharge lamps, one may observe that there are certain radiations available which are not visible, or they are in the zones where they are not normally visible. They can be made visible, and that is the effect of fluorescence, which is quite often used in our day-to-day life. So, we can see here, we say that the combination of luminescence and fluorescence increase the efficiency. When we are talking about efficiency in a lighting system, we are talking in terms of the light output in per every watt of energy that is consumed. So, it says increase efficiency far beyond incandescence. Now, what is a discharge lamp? In fact, in this lecture we are categorizing the lamps employing both electroluminescence or luminescence and fluorescence both together under the category of discharge lamps. As we go along, we see that fluorescent lamps are not any different from discharge lamps, but the phenomena of obtaining visible light is different between the two. Discharge of electricity through a tube containing a conducting medium leading to electron flow. So, essentially what you have, a large tube in which there is a gas which is ionized and made conducting. That is why we say it leads to a large electron flow. We know fundamentally any conduction is the process of electron flow, and the field is applied. And as already told, of the three processes, in fact incandescence is the one which produces light radiation output in terms of energy, which is quite close to the natural light, that is sun, and a continuous spectrum is found, whereas discharge lamps tend to give you a line spectrum or a band spectrum. So, this amounts to saying that in order to have a good radiation output, one needs to have a large amount of electrons available. So, all these lamps depend on electric discharge between two electrodes which are maintained. Needless to mention, as I have been stressing earlier also, the electrodes per se could be similar to your filament in a incandescent lamp. So, electron emission is fundamental to the whole process. Now, how does this electron emission take place? This electron emission can take place through a variety of processes. In fact, the first of these is what we call electric field emission, that is emission of electrons sheerly by application of electric field. These are also called cold cathode lamps. In fact, all of us who have gone through one course on electronics know that if you have a gas tube with two electrodes placed, one positive and another negative, we call the positive electrode as anode and the negative electrode as cathode. It is the negative electrode which emits the electrons and thereby are directed toward the positive electrode, forming the conduction current in a gas tube, and the electric field emission essentially depends on the pulling out of electrons by the application of high potential. And since the cathode is not heated, the lamps employing electric field emission are termed cold cathode lamps. They need to operate at a high potential. Another issue which often comes is the length of the discharge tube. Remember that once the arc strikes, anybody who has done a little bit of electrical engineering knows that arc is a sort of a constant current phenomena, and therefore it has a tendency to have a reasonably small voltage drop, and therefore it is, you can find that if you have a cold emission, it has to be at a higher potential, and therefore length of discharge tube also becomes reasonably high. And remember that the length also gives an idea of the length of the source or the radiation output. On the as opposed to cold cathode, we do have what's called as a hot cathode lamp, which in fact uses thermionic emission, and which has been the traces of gas tubes working in as switches in the very beginning. In fact, these electrons are emitted even at a low voltage by heating, and invariably these electrodes or cathodes are made of barium or strontium oxide on a base of iron or tungsten. So, we have electric field emission or cold cathode lamps. They need high potential, and the hot cathode lamps, thermionic emission, which can even operate at a reasonably lower voltages. And there is yet another process by which one could do, that is by subjecting the cathode to photons, photoelectric emission. Striking light with light radiation of photons, emission is achieved. These are the three processes, and in fact, as already told to you, the spectrum obtained from these discharge lamps is not continuous like an incandescent lamp, and therefore is not very close to the natural sunlight, and may not be all that good in sense of being able to observe the objects in the real sense. Remember, when we are trying to get fine details, it may be necessary to get the complete picture. That means there are other parameters that need to be included. However, the discharge lamps have been applied initially in the street lighting, and in the early days the street lights were basically operated in what was called as a series mode. If a street had about 10 lamps, the idea would be these 10 lamps would be in a series connection, that the entire voltage is dropped. So you could in fact 10 tubes together in series were operated at a from a single source, they could be operated at a high potential. Therefore, you had what was called as a cold cathode scheme there, whereas these days when you are operating most systems, in fact when we talk of a system these days, we talk about operating a system at a particular voltage, at a particular frequency. That means we try to operate at a constant voltage mode. Therefore, you may have to operate at lower voltages, and therefore thermionic emission is more or less the order. Now, in these lamps, what do we have? We have a gas or a metal vapor which is made luminous by an electric discharge. Now, how does the discharge arise? After vaporization of the gas, it is by the conduction. Now, the conduction could take place by the electronic emission, which could be field assisted in the case of or electric field emission, which is the cold cathode kind of a thing, or hot cathode thing where thermionic emission, the heating of the filament, does the trick. Now, when we saw the incandescent lamp, it was more or less giving close to white light, similar to the sunlight, which was possible and continuous spectrum. However, when these gas vapors are made luminous, of course, when we say incandescent lamp gives white light, we assume that the envelope or the bulb in which the filament is enclosed is transparent in nature. No doubt, in order to get various kinds of colored lights these days, several colored glasses are employed. Now, for a gas lamp, therefore, color or intensity depend on the gas or vapor. It is the gas or the vapor that is employed decides the nature of the or the color of the radiation. For instance, when you have a neon lamp, neon gives rise to a red color radiation. On the other hand, if you had a helium, we would get pinkish thing, and mercury is known to give bluish color, and the sodium vapor, which is quite often being used these days. Sodium is a metal vapor. In fact, you have mercury or sodium, which are metals, which are essentially vaporized state you give. Now, these are not normally gases. Mercury is a liquid, sodium is a solid which is vaporized. Now, the intensity of the radiation is no doubt proportional to the current. Now, among the common gases that are used, neon, mercury and sodium. In fact, we have observed neon being used extensively for the display purposes, signboards, street marketplaces and certain important buildings. Mercury and sodium have been extensively used. In fact, they are used for street lighting and some large industrial lighting. As already told, cold cathode is one which depends on application of the high voltage and emission, pulling out of the electrons from the cathode. No doubt, because of higher voltage application, there is intense energy consumption at the cathode, and as a result, sometimes there is every likelihood of disintegration of the cathode if there are high velocity positive ions, and all this also leads to what we call the electrode drops or the potential drops at the cathode, and this sometimes leads to blackening at the electrode tips. As we saw, we recall in the case of an incandescent lamp, due to vaporization of the filament material, due to the convection currents, we could see the tungsten deposited, especially in the what we call vacuum lamps or type B lamps. The tungsten gets deposited on the top of the envelope, and this could be taken care by introducing certain rare gas like argon. This blackening of cathode and therefore calls for long discharge tubes, and so keeping this in mind, we look at the mercury vapor lamps which are extensively used. There are two categories of discharge lamps which are important. One is mercury, the other is sodium. Mercury, in fact, because it's got the radiation located around blue region. In fact, light due to mercury vapor is bluish green and it's deficient in red rays. Because of which the color rendering is very poor. Color rendering we will understand when we go into another lecture. It means, supposing I keep an object in an incandescent lamp which is normally red in color, I would observe that to be in red. What do we mean by a red color object? It basically absorbs all other colors in the spectrum and reflects red color radiation. Now, because of the nature of discharge lamp radiations being not a continuous one as in the case of an incandescent one, they tend to do not give good reproduction of the color of the object. This is what we call by color rendering, and the color rendering is talked in terms of a qualitative as well as quantitative indices, which will be taken up at a later point in one of the lectures, and therefore it's also known to distort colors. In a mercury vapor lamp we have the oxide coated cathodes, and we do use, in fact it becomes necessary to avoid blackening and avoid long lengths for discharge tubes, and to be able to operate at low voltages to employ thermionic emission. As I told you, the two processes that are possible are cold cathode and hot cathode, and this can be taken care by having thermionic emission. We have tungsten wire filaments based on electrodes which are made of strontium oxide or a barium oxide located at the opposite ends of a glass tube. That is the philosophy. So, we have two electrodes, because remember that the supply or the electric supply is alternating in nature. So, the two electrodes alternate as cathode and anode. This has to be borne in mind, and thermionic emission needs heating of the cathode. This heating is obtained by a coiled tungsten wire, which essentially is similar to the filament in an incandescent lamp. This is why in the last lesson we were stressing often that the understanding of a incandescent phenomena is very important, and thermal radiation becomes fundamental to all kinds of sources that are employed. So, what we see is a mercury vapor lamp is essentially a discharge lamp which contains a liquid mercury which is vaporized on application of the voltage, and on application of the voltage, apart from the field being created, there is a thermionic emission because of the heating of the filaments at either end. And as already said, this has got a characteristic bluish green color, and in fact is a line kind of a thing. What is observed as far as spectrum goes is that with the increase in pressure of the mercury vapor, the band or the peak radiation shifts from bluish green to yellow green. Yellow green is incidentally our sensitivity of the eye is at a maximum. That is why high pressure mercury vapor lamps are preferred. Now, this shows a picture of a mercury vapor lamp. In principle, though it says it is a mercury vapor lamp, this is the complete scheme of components available in any discharge lamp. What one sees is there are two electrodes which are called the main electrodes. As already told, they could be made of barium or strontium oxide on a tungsten base. Then along with they will be having coiled tungsten wire filaments which heat and release the electrons when a particular electrode acts as a this thing. Now remember, mercury is in liquid state and therefore mercury is vaporized and the discharge takes place within the vapor. So we do have a starting electrode in the diagram given there S, through which the current is controlled by the current control resistance, and the other condition that is necessary for an arc to occur is the voltage being enhanced. This increase in voltage is obtained by the auxiliary, which is often known as ballast or choke. Ballast, why is it called ballast? It basically takes care of raising the potential across the two electrodes, and subsequently it maintains a constant current across the arc. In fact, the current remains more or less constant during the discharge process and the radiation is obtained. However, we, as already told, our supplies are all constant voltage. So this difference of voltage acts as storing energy in that and ensures that constant current is maintained even though there are certain minor variations in the supply voltage. So no matter what is the discharge tube, all of them have these components. So you have two electrodes, maybe a starting electrode. In fact, the we do find when we move on to sodium vapor lamp that to vaporize the sodium we create a initiating process by having initiating gas as argon, small amount of argon, which has a low ionization potential, which ionizes, and thereby because of those ions we have a secondary emission or ionization of the vaporization of the sodium, and we have the ballast or auxiliary there in the thing. So starting electrodes are connected. Initially there is a connection between the starting electrode and the lower electrode, and so that is how mercury at the desired vapor pressure is already maintained. I have told that the mercury in the liquid form at the desired vapor pressure is located in one corner of the tube, and pure argon, as I told you, there needs to be some way of initiating the vaporization process. This vaporization is obtained by having another gas which has got a lower ionization potential. We have seen this was used even in incandescent lamps, and that had enabled in reducing the what you call blackening of the lamps. Now we find that, as I told you, this has got a line spectrum with bluish green. Its radiation color improves because it moves to the center of the spectrum, which is closer to the peak sensitivity of the human eye. If you look at the lamps that are available, we find that they are in the standard ratings of 100 watts, 250 watts and up to about 3 kilowatts. As already told, most lamps are talked in terms of the wattage of the lamp, and the voltage is more or less known to be constant. Nominal voltage of most of our lamps has to be 220 volts, which is the single phase supply which we use, and this is the wattage. Once we know that this is the energy it consumes, depending on the nature of the lamp, we know what is the efficacy and we can work out the light output. This mercury vapor lamps are known to give about 35 lumens per watt with a voltage as low as 20 volts across the electrodes and a current of about 5 amperes. See, initially the arc is basically because of the argon, and this may last for about 2 minutes with a bluish glow, and later on the mercury vaporizes and takes over. Now depending on the thing, the early day mercury vapor lamps would have very large run-up time. Run-up time is basically the time required from the time you switch on till the time when mercury takes over. Okay, this could be as high as 30 minutes, but today we have powerful lamps which can pick up in no time, that is in 2 minutes. And the ballast reactor or the inductor we have shown, it's also called as choke, ballast, nothing but a inductance coil, oftentimes air core, whereas we will find when we go to the fluorescent lamps which employ the fluorescence phenomena, it must be mentioned that they are also kind of a discharge lamps only. They are, again, it is the mercury vapor, and they limit the current, and being inductive in nature, the power factor is low. We find the power factor is around 0.65 to 0.7, and oftentimes capacitors are provided across to improve power factor. Let us recall, the power factor essentially tells us how much reactive power is required from the system. Now, if the power factor is low, which means for the same power output more reactive power is required, number one, which in turn translates as higher line currents. Higher line currents would mean higher cross section of the conductors or the wires. That means not only higher cross section of the conductors and higher currents, but it also means larger drop in the lines, which means there is a danger of the lamp not lighting up for want of a required voltage. These are some of the issues one has to keep in mind. Now, let us look at a typical 400 watt mercury vapor lamp characteristics. You can see typically the time in minutes is marked. As you can see, the horizontal lines, there are three horizontal lines for the voltage, current or power curve, essentially show the steady operation. As can be seen, this particular lamp has about 7 to 8 minutes of run up time, where the current builds up, the voltage takes over and maintains at the constant level of 120 volts drop across the thing, and we see power consumption is around 400 watts. Now, these are the voltage current relationships, the three curves. You can see the current stabilizes around 5 amperes. The this run up time is what we mean by the time from the time you switch on to the time when the arc is established. Unless the arc current develops, there is no radiation. That period is the dark period. Then the other issue which is often taken care or needs to be taken care is, should there be a power failure? I mean, should there be a power failure or you switch off the lamp, now does it immediately restart, or it has to start from cold condition? In fact, most discharge lamps need to start from cold. Therefore, there is what we call a restart time. If you look at the manufacturer's catalogs, you will find startup time or run up time and restart time. Having said all this, these lamps are quite suitable for factory lighting, exterior lighting, flood lighting or street lighting. When we say factory lighting, it is not suitable for all kinds of factories. The assumption here is this is a large scale factory where the large objects are being built, where you really do not need good color rendering. Color rendering is poor, I said. Street lighting, exterior lighting, and as already said, they may need typically 5 minutes of cooling before restarting the whole process. And it's been found that this mercury vapor has one band spreading around the 500 to 570 nanometer spectral wavelength range, and at another band of radiation located between 300 to 400. Recall that the entire visible spectrum, entire light spectrum can be divided into 3 zones. 1, the ultraviolet zone, 2, the visible zone, 3, the infrared zone. Now, supposing we make the ultraviolet zone available for visible spectrum, convert into visible spectrum, it would be quite useful for our applications, and that is what is done in a fluorescent lamp. But all of us are also aware that UV lights have been used for therapeutic effects. In fact, most of us are using the water purification systems these days which are based on UV light, and for therapeutic purposes these were available as combination lamps where UV plus visible light were put together, and these were called sun lamps. They were used for therapeutic purposes, and this assumes that the mercury radiates around the thing with a peak around 365 nanometers UV region. Now, this lamp does not have any material which uses fluorescence. That is the difference between this sun lamp and the fluorescent lamp. Fluorescent lamp, what we call, has some phosphors or fluorescent material coating the interior of the glass envelope, and thereby this radiation, when it strikes there, becomes visible. That is the process by which the light is absorbed at one wavelength and re-radiated at another wavelength. That is what we call fluorescence, and in fact sun lamps are used for therapeutic purposes. So, we have seen that in essence a discharge lamp works on the principle of electric field emission, and which is made conducting. The electric field emission could be using a cold cathode condition, that is by sheer application of high voltage, or hot cathode condition wherein you apply very high where you heat the filament and thereby release the electrons. Now, and make the vaporized gas or vapor conducting. As already told, the gases that are normally used is neon, which is extensively used only for display signs. Then the mercury vapor lamp we have seen, which is often employed for exterior lighting or flood lighting. Now, the requirement to move from incandescents to discharge lamps have been: 1, to be able to operate at a lower temperature and get higher radiation efficacy. That is the very important genesis. Remember that the same kind of output from an incandescent lamp would call for immense temperature rise in the environment. Having said that about mercury vapor lamp, let us look at the sodium vapor lamp, which is just as high pressure mercury vapor lamp. Just as it has been in the high pressure mercury vapor lamp, instead of mercury we have sodium. Mercury was in the liquid state. On the other hand, sodium is in a solid state which can get vaporized pretty easily. This is sealed, hermetically sealed in a glass tube, just as it. Now, here again we have 2 electrodes, one which can act as cathode and anode depending on the half cycle to which it is applied. These are made of elliptical foils of molybdenum, and you have barium oxide coated tungsten on top of this, on the base. This is the electrode, and so if you have, recall the picture we saw of the discharge tube, one half cycle, tungsten at the top acts as cathode, molybdenum with the bottom acts as anode. That means each of the electrodes recall that they had a foil of molybdenum and barium oxide coated tungsten. So, the tungsten acts as the cathode and molybdenum acts as anode. If the tungsten at the top acts as cathode in one half cycle, molybdenum at the bottom acts as anode, and in the other half cycle the whole process reverses. The metallic sodium is placed and there is a starting gas. In fact, in the mercury vapor lamp we had argon as the starting gas. Here we often have neon gas. Those of us who have been living in metros have seen when the street lights which are employing sodium vapor lamps are switched on. If you happen to be there, say in winter time around 5:30 types, you will observe the lamps glow reddish to begin with. This is because, as already told to you, the characteristic color associated with neon discharge is reddish, and that is what is observed. And we have already said the sodium has a characteristic color of yellow. Now, this is not a cold cathode kind of a emission. It calls for thermionic emission. The cold cathode emission is normally not adapted. The reason is very simple. You need a very high starting voltage, number one. Number two, very high starting voltage. Number two is there could be large potential drops at the electrode tips, that is cathode or anode, and this could be counterproductive in terms of the life of the discharge tube, and therefore the thermionic emission is more or less the order, and therefore heaters are required to preheat the filament and these heaters are part of the lamp. In fact, we will know that the accessories required for a fluorescent lamp may be placed outside the lamp, whereas most of the things are inbuilt within the discharge lamp. As far as mercury vapor lamp and sodium vapor lamp, luminaire comes with complete housing where all the accessories can be provided. The point to be noted here is heaters are part of the lamp. It is in the gas envelope itself. Now, so it starts with a red color because initially the neon vapor has a neon discharge takes place. Subsequently, when the sodium vapor takes over, you find characteristic orangish yellow arc, and in fact this being in the central region where the sensitivity of the eye is a maximum, it has got a good application efficacy, but remember this also gives a line spectra. These are some of the issues to be kept in mind. Now, let us look at the various sources we have seen and how their energy distributions can be considered and what sort of efficacy is there in terms of a light considering the response of eye. Let us look at the natural sunlight. We have three curves shown here. One is the relative energy distribution of the sunlight. It is marked in terms of the percentage, the peak percentage corresponding to the maxima around yellow green zone. One could see carefully that it is that is more or less flat over the visible zone, and on the other hand the response of eye is marked as eye sensitivity, and there is a third curve which is a hashed curve. In fact, there is a legend which says the hashed region corresponds to the theoretically visible energy. This is the energy visible due to sunlight to the human eye. The eye sensitivity curve tells us the response of the eye to various colored lights due to the So, how does one obtain the luminosity of sunlight? this could be called the luminosity of sunlight. One obtains by multiplying the relative energy distribution curve with the eye sensitivity curve, and that is the thing. So, in principle the overall area is the idea of energy of the radiation that is made visible. So, it is very clear that the most of the energy that is available is it's continuous. I mean, you are able to see throughout the spectrum for this sunlight. Now, let us look at this for a sodium vapor lamp. The sodium vapor lamp, what do we observe? In fact, the eye sensitivity curve, bell shaped curve, which we saw in the previous one, is still there with a peak around 550 nanometers. Now, what do we observe? Between 560 to about 610, you have a histogram. The bigger one corresponds to the total energy distribution due to sodium vapor lamp. That means this is the region where the radiation due to a sodium vapor lamp exists. And when you multiply this with the eye sensitivity curve, this results in considering the overall energy, and on a comparative basis with respect to the sunlight, the hash zone which shows the theoretically visible energy. Now, having got these two, one can talk in terms of the utilization of energy of a source. That is what is, we never talk of a utilization of energy of a source because more or less the entire spectrum is usable in case of a sunlight or an incandescent lamp. But as regards the discharge lamps, we talk in terms of that. You could observe that the very little portion of this sodium vapor radiation is not usable. This will become clearer as we go along. This is for the incandescent lamp. We have seen the relative energy distribution. As can be seen, higher the wavelength, higher is the energy available, eye sensitivity. So, you find that it is more or less usable energy is somewhat similar to what we obtain in the case of a sunlight, whereas the low pressure mercury vapor lamp has two bands, one in the UV zone. In fact, that is why we were talking about the UV zone, and the other in the yellow green, bluish blue yellow green region. And the eye sensitivity, you know, the previous curve, the bell shaped curve, and seeing the whole thing, we find that there is hardly any energy available, radiation usable in the initial initial zone, which is falling mainly in the UV spectrum, whereas in the mid region we have. So, this is how one could talk of utilization of the energy of radiation available. That is why we said for the sodium vapor lamp we do have a very high level of utilization, very little energy is left unutilized. When you come to look at the high pressure mercury vapor lamp, we find on a comparative footing to the low pressure mercury vapor lamp is a little more because it has shifted from a little bit more towards the central zone where the eye sensitivity is a maximum. So, having said so much, what is it we have seen? We have seen that the discharge vapor lamps are no doubt having good efficiency in terms of light output, but the utilization point of view of the two commonly employed discharge vapor lamps, that is mercury and sodium, it is a sodium which has got a higher utilization factor, and therefore it is fast replacing most such applications where mercury vapor was in vogue earlier. Now, all these lamps are employing the conduction through the vapor or gas, and therefore it calls for vaporization, and therefore they are requiring having a starting gas which was either neon or argon, argon in the case of a mercury vapor and neon in the case of a sodium vapor. Now, since arc discharge phenomena is a constant current phenomena, to maintain the current level with minor variations in the supply voltage, there is a need to have some kind of a impedance in series to control this, and that is obtained in the form of a ballast or a choke. Now, the emission per se could be cold cathode, hot cathode or photonic emission. However, we said cold cathode relies on very large voltage being applied and has large drops at the cathode or anode end known as electrode drops. Therefore, not a very convenient thing, and hot cathode is more or less common. And most of these, the moment you say hot cathode, you have some kind of a filament which is heated by the passage of current. So, these are some of the accessories that are necessary. So, in essence, we observe that the luminescence is what is being used in all these discharge lamps. They have the electrical action on a gas or a vapor producing radiation. Now, we saw the radiation has a certain color. It is not a continuous spectrum as it was in the case of a natural sunlight or incandescent lamps. It produces a band spectrum or a line spectrum. Now, the color per se depends on what? Depends on the material used. We saw that if you use a neon gas, we get reddish. In fact, to get other colors, as already told, even in case of an incandescent lamp which gives out clear white light, is to have envelope, glass envelope which is made of different colors. The combination could give the required color. However, since the spectrum is not continuous, the color rendering is not good. Color rendering is nothing but reproducing the colors of the object in totality. Color rendering is very poor and color distortion is high in these discharge lamps. Fluorescence is the radiation obtained at one wavelength and radiated at another wavelength. In fact, this is what we observed, that when we saw the spectral energy output from a mercury vapor lamp, we find that it has a band in the UV zone as well as a band in the mid spectrum. Now, we find that as such a discharge of the radiation is utilizing only 50%, close to 40 or 50% of the energy radiated available, as we know that our eyes are not sensitive to UV. Our eyes are having maximum sensitivity around 550, 560 nanometers. This being the case, in fact, fluorescence will be the topic of the next lecture, which is nothing but again a discharge lamp allowed to radiate in the UV zone. We saw that both low pressure and high pressure mercury vapor lamps do radiate in that region. In fact, that is where your sodium vapor lamp was scoring, because its radiation is centrally located with the peak sensitivity of the human eye, and therefore utilization factor is higher. Now, the combination of luminescence and fluorescence gives much better efficiency. This is the reason why we say we get better efficiency. In fact, when we look at the fluorescence, we will make a calculation of every watt that goes in, how many watts are really used up in getting the useful radiation output. So, that will become more clearer then. Further, discharge lamps, as already said, is by the process of discharge of electricity through a tube containing conducting medium. This medium is either a gas or a vaporized metal. In case of mercury, it was a liquid metal. In case of sodium, it is a solid metal. Now, types of electronic emission, as already told, could be electric field emission or the cold cathode emission, which calls for application of a higher field, thermionic emission by heating or having a filament or a heater which heats the cathode and thereby gives photoelectric emission by striking electrons light on top of the thing. In a discharge lamp, now the gas or vapor becomes luminous, and we already seen that the color or intensity depend on the gas or vapor used. Now, depending on the current, you get the radiation intensity. Now, remember, the discharges in a mercury vapor are fine, whereas discharges in neon or sodium vapor are continuous and thick. So, the two commonly employed discharge lamps are mercury vapor lamps and sodium vapor lamps. In fact, all of us have heard the term zone lamps very often. Now, mercury vapor lamps, as already said, characteristic bluish green color is what they give. As we have known that the gas vapor decides the type of color. In a mercury vapor lamp, a starting electrode is provided and typical run-up time could be anywhere from 30 minutes to 2 minutes, I said. Here we have written 2 minutes because these days technology is available to start quickly. Gas at high pressure does improve the color rendering because mercury vapor lamp radiation shifts to the mid spectrum. With sodium lamps, a preheating heater is provided, and as the initiating vapor is neon, we get a red color which turns to characteristic orange yellow color. Some of the questions that may be answered based on this lecture are: what are the different electron emission method? What method is employed for mercury vapor and sodium vapor lamps? What are the commonly used gases in discharge lamps? What are the disadvantages of using cold cathode lamps? What do you mean by run-up time? Continuing with the questions: why do we connect a choke or a ballast in series with a mercury vapor lamp? What steps are taken to improve the low power factor of a mercury vapor lamp? What do you mean by principal line? What is the principal line for mercury vapor lamp? The principal line, some of the questions which were asked in the last lecture, like what are the methods employed to tackle evaporation of tungsten filament in an incandescent lamp, use of inert gases in the bulb, adapt coiled filament. Why is it not feasible to operate bulbs at low voltages although it amounts to high efficiency? With decrease in voltage, current increases and it becomes difficult to handle large currents. What properties of tungsten make it a better material to be used as a filament of a bulb? High melting point, high efficiency, that is luminous efficacy, ready availability and ductility. Thank you.